Stavros Institute. I have a relatively long title. I'm going to talk about the antiferromagnets, and specifically about dynamics in antiferromagnets. The focus would be on chiral antiferromagnets, for which, because chiral magnetic materials are very, very intensively studied in the last decade, the last 15 years probably, I should say, and there's a good reason for that. And for those of you that are not familiar with it, I think it will be a nice surprise to see how chirality plays a significant role in some interesting phenomena. Now, this work has been, I will use work that has been done over the years with collaborators, Nikos Papanikolaou for many years, and also in Crete, and Pierre Roy in Cambridge, and also Ricardo Marcello, who was previously with us in Crete and now in Politecnico di Bari. Let me, as I assume that I am talking to people who may come from different directions, let me just start by saying that I'm going to talk about magnets. And of course, this is a system that maybe some of you are not familiar with, but it is quite widely studied theoretically as well as a lot experimentally, for reasons that you can imagine, because magnetic materials have a lot of applications. But I'm try to persuade you in the following that this is not just an example. This is not just a system that has applications, that only has applications, but this is a system of fundamental importance where problems of fundamental importance show up. But let me start by saying that there is a lot of experimental laboratories have a lot of really capabilities have been developed over the last decades. For example, to fabricate these small magnetic particles that are half a micron wide, they can be even smaller. They can be disk particles or these ring particles. And this is just examples, so you can make arrays of them. So you can really fabricate a lot of different magnetic systems in laboratories. And these are the older, say, pictures. These are the smallest ones are 250 nanometers, but they can be much, much smaller nowadays. And what you see in there, what you're interested to see is the magnetic structure. For example, when you see dark or light regions, this means different magnetization in this small magnetic particle. So in the magnetic particle, in this small magnetic particle, there is a structure, and this is complicated structure. They can be very complicated structure. And for example, you have this more recent picture here, which is resolution is much better than older times. And you see these vectors are supposed to show the magnetic moments in the particle. You see how much structure is there. And this is an example of a complicated structure. I'm going to give you more details about this later. So these are just pictures. The different colors in this picture are supposed to show the direction of the vectors. So actually, this picture shows the direction of the vectors both by vectors and by colors, just to be nicer, I suppose. This just went off full screen. For what reason, I don't know. I tried to change the. Let me see. Well, okay. Should I go to the view and make it full screen again, maybe? Okay. Now, what is a magnet? Let me start from the beginning. I'll be quick, but really talk to you about also the basics, since, as I said, I suppose some people here may just not have familiarity with magnets. The most familiar thing is, of course, a ferromagnet. We know this from everyday life. What is that? It is a material where the magnetic moments in the material are all aligned, like this picture here. So if they are all aligned, you make a big magnetic moment, and this has this effect that we know that it creates a magnetic field that attracts other metals or other magnets or repels them. So there's an order, and this an obvious order, which is the magnetic order. But now we don't only have the ferromagnets that we all know, but we also have antiferromagnets. What's the difference? The difference is that the magnetic moments in an antiferromagnet are anti-aligned. So every moment is oppositely aligned than its neighbor. Now this is magnetic order. This is perfect magnetic order, but it is not. It is an unusual one. It is also not something that you will actually feel, because every moment cancels its neighbor, and therefore there is no net magnetic moment. There is no magnetic field produced by all that. So we don't usually consider this thing in everyday life. So to say, if you find an antiferromagnet, you're not going to realize that this is something. So you really have to do some special experiment to get that. What we're interested in the following is to study excitations or structures which are not exactly this perfect ordering, but something close to it. That's basically the field. So how you describe this ferromagnet or antiferromagnet, obviously not in this very trivial state, but in probably more complicated states. Now, why are we interested in magnets? Well, because they have a lot of applications, and they're used in magnetic cards and everything. But why are you interested in antiferromagnets at all? I mean, is this probably not too special or unuseful, not useful? Well, actually, it turns out the opposite is the case. Antiferromagnetic materials are abundant. They're everywhere. There are a lot of them, much more than the ferromagnetic materials. We just don't feel them. And they have some good properties. For example, they don't create these stray fields. That is, they don't create an overall magnetic field, which is actually good, because you can pass through machines and they don't feel it. You don't destroy them. So it's a good property. But now why? And since they are so good, why have not used them yet? Exactly for the same reasons, because it's very difficult to detect. So you see, it's good because they are robust, but also they are not good because you cannot detect them. So the same reasons it's good and bad. But now this is changing, and what happens is that in the last years there are new experimental techniques, and they can actually detect antiferromagnetic order. And there are several experiments in the last years, say by optical switching of magnons, then current-induced switching of domains, antiferromagnetic domains. Also, they present dynamics in the terahertz range, which not many systems do. The terahertz, you have systems in gigahertz, but not in terahertz so much. And well, we have various observations in the last years. That's my first argument. The second argument is about chiral magnets. Now, chiral magnets means there's something where you have in a system, and then left and right is not the same thing. You interact differently with your left neighbor than with your right neighbor, roughly. And you might say, well, this is probably not the first thing that comes in mind. Usually we think that symmetry is the first thing, the most common thing in nature. Turns out that many magnetic materials are actually chiral. They have been predicted like probably 60 years ago. People did not believe it for maybe 40 years, but in the last 10 or 20 years, they tend to find them everywhere. They tend to detect chirality in magnets all the time. This has happened with ferromagnets, because most experiments, the overwhelming majority is with ferromagnets. But there's good reasons to believe that the same thing will happen with antiferromagnets once we get more advanced to do more and more experiments. And there are already some observations with chiral antiferromagnetic materials. So antiferromagnets is my first argument, and chirality is the second argument. Therefore, I go on to a model, a minimal model for chiral antiferromagnets. How do you describe them? I have some formulation here that I want you to have a look, although obviously I'm not going to go into the details of the calculations in the next, in the following. But the first thing you do is you assume there is what we call exchange interaction. That is this, every spin in a square lattice. I'm thinking of square lattice, a two-dimensional system, typically. Every spin in the square lattice position ij interacts with its neighbors, which are in i+1 or j+1, the right or top, obviously to the left also and to the lower. And that's called exchange interaction. Okay, now there is also a different interaction which is also exchange, this second one, where each spin interacts with its neighbors, but in a different way. And this is a chiral interaction because of this external product. So it's an anti-symmetric interaction. The first one is symmetric. The second one is anti-symmetric. Turns out this is chiral with this triple product. And now there is a third interaction because we are in a condensed matter system. Usually not every direction in space is the same because your film is cut in a certain crystallographic axis or something. And you also have anisotropy, some anisotropy, which is in this case, say, in the third direction. Somehow the energy is favored by the spin pointing in the third direction. This is the third component of every spin vector. So we have three interactions. I hope I gave you the flavor of each interaction. The exact formula does not matter very much for us here for the moment. Now you go to the equation of motion, and well, this is not a trivial task to get it. It is usually called the Landau-Lifshitz equation. But the important thing is to see here that you get something which is like a force by the derivative of the energy with a spin, with a variable. And then this comes here in the second right-hand side of the equation. In the left-hand side, you have the time derivative, the first time derivative of the spin. So that's what's happening. Now, we have a problem now. The problem is that every one of these spins is roughly oppositely aligned with its neighbor. Therefore, you cannot just say, I'll give you an overall description of the system. You cannot say, I'll give you a continuum description of the system, as we usually do in most systems. We don't look for every, I mean, for example, in molecular dynamics or something, you don't really look in every molecule what they are doing, or in chemistry, every single molecule. That would be a huge task. You want to have an overall in fluids. You want to have an overall picture of the thing. Here, you cannot get that, because if everyone is totally different than its neighbor, what's the overall picture? So there is no obvious continuum limit for this system. And that's our problem.
Does this correspond to the ferromagnetic?
Yes, yes, because the ground state is kind of easy to find that it is antiferromagnetic, because this interaction here, it's good to have this S just opposite to that S and to that one, and therefore all the neighbors opposite the magnetized, they give you minimum energy, like maximally negative, so to say. Yeah, yeah. So this gives you that. Yeah.
I get the antiferromagnetic part where you must opposite spin. How do you define the chiral? You say the presence of spins, or is it?
This is the chiral thing. So, for example, you have to go into this term, and suppose you propagate along the I direction, the X direction. You have to have that one at the right angle to that one in order to get a minimum for this term. So you have to have the spins rotating in a certain sense, say in the positive sense and not in the negative, because the external product has this property. Yes. Right. Yeah, good thing. No, in this case, the material is chiral. So it's an intrinsic property of the material. And this is something that, as I said, I want to repeat it, has been predicted in 1957. And people didn't care about it for 50 years. And now we realize that many materials have this property.
So the ground state is this term zero?
The ground property now, this term is actually zero, but I will come back later to it, because there is a case where the ground state is defined by this term, and therefore it's not what we call the antiferromagnetic state. So there's some structure to it. There are things to say there. So the trivial solution is indeed that they are anti-parallel, and this term is minimum and this is zero. But there is also a different case, and I'll come to it. Let me not.
This chiral is coming primarily because of temperature.
And it's not, no, it is intrinsic. It is due to the crystal structure of the material.
It's really also.
And he's going to look at the same time in magnets between permanent magnets and the ferromagnetic magnets where you have an electric current driving the magnet.
Yeah.
Here you're saying that this chiral is intrinsic, it's something that's permanently integrated.
Yeah.
And there will be no need for an external influence to drive the chiral.
No. This is a chiral material, so it has this magnetic character. The what?
The shape of the geometry.
No, the material might be, it is the crystal structure that allows for the magnetic chirality.
What is the reason that it's the system is at all with the grounds in some different state? It is not.
No, it's. Why? Well, I mean, you can go above the background state. Okay, so well, obviously, if you have temperature, of course, you excite different modes. Now, you can also have excitations which are not the ground state, but they are stable.
Okay,
and I will talk about them.
There are some excitations.
There are some excitations. Yeah, I'll talk about these things. Yeah.
So since there is this having the act with the Hamiltonian, I would assume that chirality cannot be broken spontaneously, right?
Chirality can be broken.
Cannot.
No, but it is broken. So you can create. I'm not sure exactly, but you can construct a configuration which is energetically favorable, which is chiral. So, for example, a rotation of the spins in this sense and not in that sense. And yeah, I'll get to that. So let me go a bit faster. For example, this is the system, how it would look like in an artistic sense. That is, some sides are open circuits and some sides are dark circuits. That is, somehow the spin, you can imagine the spins in the open circuits point towards you and the spins in the dark circuits point toward the board. And that's the system you want to describe. Okay, now let's start from that. You actually have two sublattices. You can treat them separately, for example. That would be an idea. Now, I think we had a better idea, and we say, I have this is my lattice, the open and filled circles, and I consider tetramers. So I get groups of 4 of them. What can I do? Well, I call these spins A, B, C, D, depending on where they are in each plaquette, and I don't consider any more the A, B, C, D, but I consider all 4 linear combinations of them, which is A plus B plus C plus D, or A minus B plus C minus D, etc. And I work with these fields. Why? Well, because, for example, the M is more or less the local magnetization, because it's a mean magnetization in this area. Now, the N, you see it is A minus B, so you subtract spins which are roughly opposite to each other. And C minus D, again, C minus D, they're opposite. Therefore, you create something that over the plaquettes, from one plaquette to the other, is kind of the same thing. I mean, they don't, from one plaquette to the other, the M and the N and the K and L do not change much. They're roughly, so you now consider M and K, N and K and L, and you're going to build a theory on these fields, not on the spins. That's a long story, and the only thing that one has to keep in mind here is that this M is going to be small, because of course, as I said, they are almost oppositely aligned, the neighbors, and you add them, but then N is going to be big, because you subtract A minus B and they are opposite. So it's like subtracting A1 from -1, you get a 2. So that's what's happening here. And now you assume some mathematically good properties, that you have some continuity in some variables, you use Taylor series, and then you go to the M, K, and L variables, and you get a model. So I skip all that, of course, and I give you the model. The model is this one here, and the surprise is you write a model entirely in terms of N. All other fields have disappeared magically. I'll show you what happened to them, but now you have only one field. This is N cross N double dot means time derivative, and this field has this form. This is the exchange field, which is a usual in, say, field theory, and that's everything It's a kind of Laplacian, and this is a first time derivative, space derivative, and this is an isoc. There is only one remaining parameter in the model. Yeah. The neighbors are with a minus sign, so they are subtracted. That's the idea.
So there are lots of magnetization and just to get some insight on what the mean.
Yeah, it's like, you know, you have up and then you have down and then you subtract them. So you get, if you subtract this from that, you get something up. Yeah, it's a good sorry. The n in the ground state is 1 because yeah. But that's one of the problems that I'll pose later because there is an issue, mathematical issue about that. So now, yeah, we have this parameter. The two big surprises here are first, as I said, only n here, and second, well, actually, this is second time derivative. I mean, we started with equations with only first time derivative, and we end up with second time derivative. We actually started, since some of you are in particle physics, etc., we started from condensed matter, and we end up in particle physics, because there's something strange about this here. So this model is the so-called sigma model, which has been discussed a lot in high energy physics. But here you see this with particular magnetic interactions in a magnetic material. It's a so-called sigma model. And now, just to maybe definitely you will be curious what happened to the other variables. It turns out this m is proportional to the n dot time derivative of n, and then k and l is just the derivatives of n. All that, of course, is to a first order in asymptotic series. So there are some approximations here, but we can forget about them from now on. I mean, this kind of point of view was developed in the former Soviet Union, mostly in Kharkov and Kiev, quite a few years ago. And what we contribute to that is actually to use these tetramers, which there was a problem in this theory as it was developed here. So we solved this problem. But this is not important for the moment. Yeah. Oh yeah, this is right. Yeah, well, it's yeah, no, I don't know. It's the time derivative of n. Is there a physical meaning to that? Yeah, good question. I don't know. Probably not. So it's effective. Was yeah, it's like a force. I mean, not exactly. Yeah, but here the theory is written in terms of the Nel vector. The n we call the Nel vector. So it's not directly related to the magnetization or the magnetic field. It turns out from this construction that actually the m dot is related to the magnetization and thus to any magnetic field that could be produced. So dynamics is connected, and I'm going to talk most about dynamics. Dynamics is related to the magnetization. As I said, also to magnetic fields. That's what I want to sell to the experimentalists, that to observe these things, they have to go into the dynamics. Without dynamics, m is 0, so you don't really observe anything. I mean, at least with the usual techniques.
So if I mean dynamics, we expect an external precipitation,
it's a, yeah, well, no, you have to somehow excite dynamics. You have to excite it. Yeah, you will have to excite dynamics somehow. Now let me come to something that is very close to what Vangeli said earlier. What is let's solve this model. One obvious solution is n is constant. N is constant, there are derivatives there, so you all go away. This is always a solution. In fact, n has to be proportional to the. All right, when I push this continuously, it goes from full screen to non-full screen. So n has to be due to the anisotropy that I considered along the z-axis, the third direction. Okay, this is a detail for us here, and this is always what we call the polarized state. It's exact the Nel state that I initially showed to you, the trivial state. That's described as n is equal to a constant vector. That's always a solution. It turns out it is the ground state, but only when this parameter lambda is smaller than some value, which in these normalization is 2 over pi. When you go to larger chirality strengths, that is lambda larger than 2 over pi, then there is a new solution to the system. And this is called a spiral. Why? Because you see this n vector rotating as you propagate through your material. And that's now, it's called a spiral. You have to imagine that the spins as you advance here, rotate in a certain sense continuously. Now, it turns out this non-uniform configuration has lower energy than a uniform configuration. And this was the big surprise for the experimentalists, because at some point they observed complicated structure in a material which was not disturbed. So this was a surprise. And then the whole hype started about chirality, and they observed a lot of not complicated structures in chiral magnetic materials. So this is called the spiral state, and it happens at the, I want to emphasize that, at a particular value of the parameter. Now, there are more complicated states. If you go now to 2 dimensions, a film, then you can have these structures, like this one here, where, of course, if you go around the center here, you see the vector rotating. So this is clearly due to the chirality, but it's a bit more complicated than that. And this is called a skyrmion. Why? Because you have to imagine that this vector shows now the projection of the n-L vector on the plane. The L vector is always a vector of unit length. So, for example, in this center that you don't see a vector, it just means it points towards you. And in this white region, where again you don't see any vector, it just means it points towards the board. So this vector now is always a vector of constant length, and the only thing you do is just you rotate in space. And in this skyrmion, what you do is there is one vector for every direction in space. So if you try to follow this, here you are on the, say, North Pole, for example, or maybe South Pole, as I said earlier. Here you go off the South Pole of the sphere because the vector is rotating, and you are in the equator of the sphere. And when you go in the center, you are now in the North Pole. So you kind of cover all directions in space, the whole sphere. That's equivalent things. And that's why this is called a skyrmion, because there is a topological number associated with this covering of the sphere. It's called the Skyrmion number, and this is covered, the sphere is covered once here, and therefore we say that this is Skyrmion number 1, and we call this a skyrmion, or a magnetic skyrmion, because there are skyrmions originally in very different theories. Now this is another skyrmion here. Okay, yeah, right. Sorry, the color means there is a component of the vector that you don't see because I've taken the projection on the plane. The color just color codes the direction, the third direction of the vector that you don't see. So here it means that the vector points towards you, for example, the red color, and the white color means that the vector points towards the board. So it's some way to encode the 3D vector. Yeah, so because this n vector, I want to say again, it has constant length, so it always, you cannot squeeze it. Now this is again a skyrmion. The only difference is that this is just bigger than that. But if you go to topology, that is to covering of the sphere, there is no difference. This again covers the whole sphere once. There's no change. There's no difference. So these are so-called topological solitons. You can have them big or small or whatever, but the topology is there always, and it has the same topological number. That means you can deform one to the other, this to that, just by expanding. But you cannot get rid of it, because if you do whatever deformation you want to this skyrmion, you can never, because you cover the sphere once by these vectors, you cannot just deform the skyrmions and somehow not cover it at all. This is impossible, but for geometric reasons, or topological reasons. And yeah.
Follow this speed.
Yeah, yeah.
Do we get physical facts?
No, I think not, because you have to. Yeah, now it's a question how exactly you do the mapping. Here, consider that you have the plane, and you do the mapping. The mapping is a vector to the sphere. If you kind of start from here, take cross over here, yeah, you get some kind of helix, some kind of rotation, the vector, if that's what you. Now, if you go around the Skyrmion, yeah, you get a full rotation. So it depends how you do the. But now it's a mapping from the plane to the sphere, so the helix is not. I don't know how you define it there, if I understand correctly what you're saying.
Which is
Yeah, the arrow. Yeah, I mean, it would be nice to have a 3D arrow, but that would get this quite complicated. Yeah, okay. So you cannot just have suddenly something that does not contain a Skyrmion, because this would only point, say, to the north pole of the sphere, would have not point in the whole sphere. And it's impossible geometrically, if once you cover the sphere, to uncover it. That's impossible. You can see this with a circle. If you have a rope around the circle, unless you cut the rope, you cannot uncover the rope. You know, there's no way to. You have to cut it if you want to. Otherwise, you always cover the circle with this rope. Okay, these are the topological arguments that got people excited about these topological solitons. And but now, okay, I think I gave you an introduction. Yeah.
Yes, we do have an idea. The phase structure of this system.
The phase. What are the different states, possible states, or what?
Like, yeah, the different states basically are temperature.
Yeah, I didn't put temperature here yet, or I will not do it. But we can have various excitations. We can have various excitations in the system, and in fact, that's what where I'm going now. I'm going to tell you that, you see, because we have a second time derivative in the equation, if you write this as a usual Hamiltonian system, you're going to get a kinetic energy, n dot squared, which by the usual formalism of mechanics would give you the second time derivative that is acceleration in the equation. So this system has kinetic energy. And there's a very funny thing about it, because you started with a system that did not have kinetic energy. It only had speeds. There was no kinetic energy in the beginning. And suddenly you end up with something which has the physical meaning of kinetic energy. That's a problem in itself. But anyway, let's believe the formulation and go on to that. So you have some kind of kinetic term. So we started from first order in time, we ended up with second order in time and kinetic energy. And there's a question of what it means, kinetic energy, for what the physical meaning is, but let's not go into that now. Since we have kinetic energy, let me now accelerate my presentation. We thought, well, we might as well have moving, propagating Skyrmions or anything else propagating. Now, why don't we look for them? So we thought, right, if there are such things, there will be solitary waves. They will have this form. That will be some function of x minus vt, where v is the velocity, propagating along, say, the x direction or whatever direction you would like to have. Now, I use this, and then the time derivative in the equation becomes space derivative, because you have this particular form here, and you have to solve this equation. There is no guarantee that this equation has a solution, but nevertheless, we solved this numerically. It turned out, by some method, it did have a solution, and we found these solutions. This is the Skyrmion with zero velocity that I already showed earlier. This is now a new solution. If you assume a velocity of the Skyrmion 0.4 in the units that we use, you see this is a bit elliptical shape, probably. It's not clear. And if it goes faster, it has another elliptical shape. The propagation is in the horizontal direction. Propagation is to the right. So there are Skyrmion solutions traveling with some velocity. And that's now a new thing in magnetism, because if you are in ferromagnets, there is no such thing. So only non-ferromagnets you can get that. And they have not been observed, if you ask me about it. Okay, this is prediction. And now there is an interesting thing. Now, how fast can they propagate? You can ask. And it turns out that numerically, that you can go for this particular parameters that we used. They go to some velocity 0.71 or some, some number. One now here is the velocity of the linear excitations of the system. This is below the velocity of the linear excitations, so-called spin waves. You can imagine phonons or corresponding of that. So this is kind of a small velocity. Why is this happening? That's a question. What actually is happening? Why can they not go faster? Well, numerically you suspect that you cannot go faster because they get too elongated. They get very elongated. So at some point, they get infinitely elongated, and this is not anymore a Skyrmion. And this appears from your numerics. Now, I can give you, well, I can skip this one unless somebody wants to listen about experimental things. I can give you an explanation for that, which I think is what I found an interesting theoretical method. You say the following. Now, let's go back to the equation. This is the equation. That's now Laplacian, this one and that one. That's first derivative is the chiral term, and this is the anisotropy no derivatives. And you say, look, if I really believe that what happens in the critical velocity is that this gets infinitely elongated, this actually means that the second derivatives along the long direction here do not matter. They get very small. So let's forget them. Neglect the y derivatives, the red terms. If I forget them, then I get this equation. Obviously, 1D, only x derivatives. Okay. Now, the velocity comes in here because this is propagating in the x direction as a solitary wave. Therefore, the time derivative has become the space derivative, and therefore there is an extra term here. But, you know, this equation is exactly the equation that I showed you earlier. And I told you that there are spiral solutions. It's a 1D equation. What happens is that when a parameter like this one here becomes smaller than 2 over p, I'm fine. But if it becomes larger than 2 over p, then I'm not fine anymore, in the sense that my ground state destabilizes and becomes a spiral. Luckily, well, surprisingly, the velocity comes into this parameter, and therefore this condition gives you that the velocity should be smaller than something which depends on the chirality. And this is smaller than 1. Without chirality, lambda equals 0, that would be 1. That's the usual case. What we say, usually we think that nonlinear excitations can go fast. How fast? Well, they can go as fast as the linear excitations. That's actually not correct. It's correct in like Lorentz invariant theories, most theories in physics, but not in general. And that's a new thing here. What happened here is that chirality introduced a new way to destabilize your system in a dynamical way. So you see, in usual theories, what happens is that, say, you know, why do you have the speed of light? Why can we not run faster than that? Because we would destabilize the universe, more or less. Or anyway, no, I'm exaggerating. Sorry, it's probably not correct. But that would create infinite energy, various things. Now, this is a different mechanism here. And that's now, okay, this is confirmed numerically. Let me not you know, bother you with that here. But I want to say the comment that the maximum Skyrmion velocity in this case is set by the phase transition from the polarized state to the spiral state. And this is a topological phase transition, because the spiral is a topological object. I did not mention that. So this is a mechanism that I have not seen elsewhere, at least myself, to get a dynamical phase transition, so to say, or destabilization of your system or maximum velocity of your nonlinear excitations. These are all equivalent things. So that's what's happening here. That was the theoretical story. Now, I do have more things to show to you, but it depends how much time we have. Because there is one more phenomenon that I could briefly tell you, but there are another 3 slides that I have that are only, I only want to mention problems that might be interesting to some of you. And I don't want to miss that because it would be good. I don't want to, to tell you all of the details of what I did. It's better to pose some problems that would be more productive, I think. So let me assume that I have like 5 or 10 minutes. Yeah, okay. So the next thing that we thought is, well, having a kinetic energy is not, we're not done with that. We can produce many more phenomena with that. One phenomenon is that if you have a kinetic energy, it's like a pendulum. You have a pendulum which goes up, down, and it oscillates. What happens is that when you're up, you have a lot of potential energy. When you're at the lowest point, you have a lot of kinetic energy, then potential, kinetic, oscillations. Why not try to have this here? Well, yeah, let's try to do it, and actually works. And what we did, I mean, in some, if I can say about the experimental way that this can actually be realized, you can apply a voltage to your system, and this actually for say 13 picoseconds, that could be very short, and this changes the interactions. So temporarily your system is different magnetically, and therefore if you have a Skyrmion, while it was happy before you apply the voltage, it's not happy anymore because the interactions are now different, and therefore it starts it's destabilizing. Now in this case, the way it is destabilizing, it becomes it starts becoming smaller or bigger. Its size becomes smaller or bigger. So you have oscillations of the radius of the Skyrmion. Here's the radius of the Skyrmion. It starts from here, goes up, down. Now you stop the pulse, but it's not in a static condition anymore. So it goes on oscillating. There is damping here, so there are damped oscillations of the Skyrmion size. We call it breathing. So it goes like that, back and forth. Okay, so that's interesting. I mean, people are interested to observe that. But why could it be a bit more interesting? Because it turns out that if you apply the pulse for 7 picoseconds, for some reason, I mean, you tune it, you end up with the following scenario. You start with the Skyrmion. This is now a very minimal representation. You don't show vectors. You only show the third direction of the N3 by some nice surface plot. So the Skyrmion is like that. Then it becomes bigger because of this destabilization. Becomes smaller, but actually it becomes so small, it becomes a spike, a singularity, and then disappears. And you can ask, how could it happen? This is a topological soliton. Why can it disappear? What happens to topology? Is mathematics okay with that? It turns out it is okay, and the reason, oh sorry, not going to that. The reason is that even a Skyrmion, which is singular, has finite energy, despite what happens in many other systems. Therefore, you can destroy it, and it is a nice mathematical problem to describe this singularity formation precisely. But this can be done apparently. Okay, so that's one of the problems that I want to pose. But I'm skipping the details. I mean, we have some arguments how this happens and all the scales and how all this happens, but I don't think it's should say this now. Okay, good. Yes. We didn't do this, but this is a good idea. So you could obtain resonance. Or
so the stable behavior, so that in general, magnets cannot keep up with in my continuum relativistic magnetism. They cannot always keep up. So my belief is that you might see some phenomena equivale that frequency.
Okay, yeah. Yeah, well, I mean, I don't have anything to say on that, but I had been thinking about periodic excitations, but we didn't go into that. Okay. So, in fact, what we did here is, maybe I should say that, we did not try to crash the scheme. You know, the intuitive, the first idea you have, okay, let me try to crash it. And we didn't try to do that. We actually applied some pulse, we tuned it, and then we let the schema go. And this was crashed by itself by internal dynamics, the spreading dynamics. So this was the suggestion to experimentalists. All right, now basically my talk is over, but I want to show you 3 topics that probably are interesting or interest to some of you, just very, very sketchy. The first problem is probably in numerical, and the question is, how do you simulate numerically this equation, this sigma model? That's not I think this, as far as I know, this is an open problem. You can do it, you know, if you want to do this sum quickly, yeah, you can do it. But there are issues. For example, you have to have this null vector field always on the sphere. That's not obvious how you do consistently. It's not. Then another thing is that this is second order in time. Again, it's not obvious which are the best variables to do that. Is this the n and then a dot, or probably not? For example, I'll tell you an idea. I mean, I started with the spin variables and derived the sigma model. Okay, now I can start from the sigma model and say, well, I want to simulate the sigma model. Okay, why not simulate the spin variables? I mean, they are supposed to be equivalent. So I can simulate the spin variables and claim that they simulate the sigma model. This is actually correct. It's to some approximation. But I'm not sure it's the best idea. So what's the best idea? That I do not know. So how you simulate that? The second thing is, okay, this is directed to the particle physics people. There are different excitations in this system. You have actually to change a bit your energies. But turns out you can have this type of excitation where this is like what we call a vortex. You see these vectors rotate in a sense. And this is the red, that means it points towards you, the vector in the center. And then this is blue, it means points towards the board, and the vectors rotate in the opposite sense. If you go around the center of this vortex, then you see your vectors rotating, not in the sense that you rotate, but in the opposite sense. And now, if you combine the two, you basically cover the sphere once. So this is again a Skyrmion, but it's a kind of, you get this one. If you take this one and you apply what we call a Möbius transformation, standard in complex analysis, you get this thing, which is a Skyrmion. Well, an anti-Skyrmion actually. But so there is a structure here. It's called the this. If this is a Skyrmion, it can be decomposed in this mathematical way to 2 parts. They call them merons, from the Greek meros. This was introduced by David Gross and co-workers in 1977. And they were thinking of explaining quark confinement this way in their models. I don't see this is going on anymore, but here we have magnetic merons. And it turns out that they have pretty much very close properties to what Gross predicted in this old paper. This is now a system where you actually find them as solutions of the full model. This was not the case in the first papers. So these are the merons. Okay, these are constants supposed to be the positions, this position here and this position here. Yeah, and the third thing is something last thing is something more recent. I found out that some people are now getting excited with some new particles that they call fractons. Why do they call it fractons? Because they say, look, we think that particles can just propagate in the way Newton described. So they just move in space freely with a constant momentum, a constant velocity, etc. They found initially in condensed matter that there are particles that cannot propagate. They are pinned, but they can propagate as long as there are 2 of them together, sometimes. So they call them fractons because it is like a fractional particle. And only when it comes with a partner, they become full particles. So they are excited about that. Now, there are a couple of examples in the literature. And one of the things that impressed me more is that you can construct what they call higher rank gates theories, some gates theories, different than the usual ones. And if you get at gates theory, turns out you get a continuity equation. And the new thing is that this flux here is a derivative of something. So here you don't have, in the usual continuity equation, you have a derivative here, a divergence. In this thing, you have a derivative of a derivative, second derivative. This gives you some properties that exactly, I'm not going to tell you details here, but because I want to be brief, but exactly give you the properties that fractons have, that is, they are spontaneously pinged, etc. So you can get them directly from this equation. That was introduced, as far as I know, by this guy in 2017. This is in a review paper here, so not many years ago. Well, actually, in magnetic systems, there is a paper by Papanikolaou and Tomas 1991 that have derived exactly this formula for the magnetic system, for the ferromagnet. And this in this case, this is connected with a topological density. It has to do something with topology. So now we have, as far as I can tell, a field that tells you there are some particles that have peculiar properties. For example, in magnets, initially introduced, that this is connected with a topology. Now, we also have similar things in higher rank gates theories that it's not clear to me whether they are connected with any topology. And there are also other examples that I'm not writing here in lattice models, in spin models on a lattice, but that somehow have the same properties. But as far as I understand, it's not clear yet formally how one is related to the other of these examples. So this is a new thing. Probably, I don't know. I mean, I only heard it recently. So probably you have not heard of that, but it looks nice. So thanks very much. That's the end of the talk. Thank you very much for your attention.
Same for the people online. You can just unmute yourself if you have a question.
Yeah, just, I mean, thank you very much, Stavros. It was really exciting. So just from curiosity, are there any clear, let's say, conservative quantities? I mean, like Hamiltonian momentum that we have the fluids.
Yes,
It's not, for me, it's a bit, it's not clear, at least because you have also the excitations, right?
Yes,
so it's,
yeah. Right. Are you talking about the model, the sigma model that I was talking all the time, or? Yes, so indeed, that's, yes, very nice. This is, if you go to, let me go back to the sigma model. Wow. You go to the sigma model, indeed, you can have a Hamiltonian formulation. For example, I said about the kinetic energy, there is a potential energy as well. Now you can also have a momentum, linear momentum. You can also define the mass of the Skyrmion in a consistent way.
So all this should be conserved quantities during, let's say.
The energy is conserved, the momentum is conserved. Exactly, yes.
So when if you perform, let's say, numerical simulation, this again is the main concern that you should follow.
That's, yes, of course, yes. You should make sure that this is conserved, and this is not a trivial thing to achieve. That's right, yeah.
And, if I may want more, just again, how large are the systems?
Okay, the Skyrmions can be, they can be like 200 nanometers wide, but they can also be 10, apparently also smaller. But then it's probably more difficult to observe, right? But apparently they can be even very, very small, even few nanometers. Yeah.
Okay, two things before I forget. One would be about 3D visualization, and the other part that I think is important is there. I mean, usually when you have these ODEs, there's also like the counterpart of doing the energy minimization. There's two ways of looking at it. Like, like in classical mechanics, there's the way of the force balance and momentum equations, but there's also the way of the energy equations and kind of minimizing the energy and all that. And I wonder whether like for the numerical part that you touched on, whether it makes sense to look at it from an energy equation where the length of the n field is an extra constraint
Yeah.
so that you can impose it more easily rather than the OD approach.
If you're referring to these pictures, for example, we found them by energy minimization. That was the method.
Like you've got the integral and then you just add minus L and then your other constraint.
We didn't know the constraint. We added in a naive way. That is, if I believe we kind of enforced it during the steps of the algorithm, which is not the nicest thing to do.
Look at it this way.
But to look at it, yeah, with a constraint, yeah.
Yeah, like the standard kind of calculus of variation way.
Yeah,
you have an extra constraint, just put it as minus an extra parameter, and then the integral of what you want.
Yeah, you could try. You have to try these things. Now, in this case, because at the end you get a steady state, it does not matter. So you don't. No matter how you do it, you do not introduce any errors. But if you do really dynamics, then this might not work. This is a steady state now. Yeah.
And also coupling these two experiments, like typically, would you have like a plate?
A film, a magnetic film.
With a magnetic film, so we would see what we see now in the slide. For can we directly visualize it as the fields of the
you see, okay, now there's a question. What are you actually looking to detect experimentally? That's something that I mean, okay, I can give you ideas, but I'm not an experimentalist, so I would not insist on that. For example, in these Skyrmions, what we know that I noticed earlier is that this produces no magnetization. This does produce magnetization, and thus it should produce also a small magnetic field, the propagating ones. Well, I could definitely suggest that you should look not in this structure, but in the magnetization structure, which is related to the time derivative of this n. I think this is a good idea. Now, it's a matter of experimental techniques. No, because it's a steady state, but there is this supposed to be this steady state. So there's time implicitly. Yeah, it's a wave. So we know what is the magnetization produced by this thing. I mean, it's not difficult to find. So
you have this film, like the normal experiments they do with, you have a plane and you put a magnet and dust it with
okay, yeah.
Small iron particles, and you see them taking conformations. I just wonder.
I must say it is surprising what techniques the experimentalists have come up in the last years. It's really something amazing. So I don't want to give them advice, really.
At this point, even these things happen now, it's in the chain.
Yeah.
Wouldn't you get any dynamic signature in an experiment, for example, let's say on I don't know on the spectrum of these things? Wouldn't you be able to detect some?
Just to excite some other mode or something.
Once you're excited, you would be probably able to measure the magnetic resistance of this thing or something.
Yeah, I have not thought about that. It might well be that if you
are they EPR these things and like resonance studies of these things?
Okay, no, I think I don't know much about it, but it is. I mean, yeah, that's a direction one should think about how to.
So here you define this velocity as clearly in a way of well, we can visualize as this Skyrmion has to be moving in space, right?
Yeah.
And you told us how this evolves. You can view it as a kinetic energy. And then in the last example with the breathing modes, there is no such thing as actual movement in space. It's just breathe.
Yeah.
So how do you combine these two? I don't know.
It's
how is
internal.
kinetic energy defined in that case? How do
No,
you
it's the same
visualize?
definition. It's the same definition, but where is the kinetic energy? Somewhere. Well, there it is. Well, no, okay, back. Here, this is a kinetic energy. As long as you have dynamics in M, it turns out you have some kinetic energy. So this could happen by propagation as a rigid propagation, but also as some breathing or some other dynamics thing. And then again, you have some kinetic energy, which is internal. I don't know how to call it. It's different. Physically, yeah, there should be differences, but the mathematical formula is the same for both cases.
If anyone online wants to ask, they can just unmute and go ahead. There are people with more questions, but I suppose they'll have some discussions afterwards. Thank you very much.
Thank you very much.